We can also synthesize the thermoplastic elastomer or TP using vulcanization process using non-sulfur and peroxide. For example, we have a block copolymer, or we call it SBS. The styrenic block copolymer, what invented by Shell Company, or Kraton. Styrene butadiene styrene, SBS tri-block copolymer, is actually manipulate with their soft and hard properties. What Charles Goodyear has invented was a permanent cross-linking. But in this case we use the combinations of hard and rigid polystyrene, where the glass transition temperature is around 100 degrees Celsius, to be the end groups. While the middle segment consists of gooey and sticky polybutadiene, in which soft and elastic. It exhibits glass transition temperature, around -70 degrees. So what we can do is the polystyrene can form a spherical domain by aggregation, and linked by polybutadiene forming a network. So basically, we are designing a polymer system that has a temporary cross-linking. If you expose it with 120 degrees Celsius by heating, this whole thing will soften up, and behave like any other than thermoplastic. We have also another type of thermoplastic elastomer, that can be prepared from block of different tacticity from one monomer. For example, we have polypropylene which contains of a tactic block, amorphous which possess a soft and elastic. But syndiotactic consist of crystalline part, which is hard and rigid, prepared by using metallocene catalysts polymerization. So what are the advantages of vulcanization? Since the polymer molecules are tied together, the vulcanized rubber do not melt when heated, because they cannot flow past each other. It also doesn't get brittle because the bonds are strong and do not easily break. It also possesses high resistance to oxidation and abrasion. So what are the drawbacks of vulcanized rubber? Since vulcanized rubber doesn't get gooey and flow when it gets hot, you have to mold it into whatever shape you want before cross-link it. Once we treat it with chemical or heating, we cannot get back the original starting material. Therefore, it is really difficult to recycle. So what happened in the vulcanization process? The vulcanization treatment is brought about by heating rubber with sulfur. Vulcanization is accomplished by a process invented by Charles Goodyear in 1839. It is such a sad story for Charles Goodyear actually. Charles Goodyear was a scientist who dedicated his life experimenting with rubber. He tried so many experiments to invent something with rubber. From a story that I read, he even took out a loan to support his experimental cost, and left his children starving sometimes. He even inhaled a lot of chemicals, until it affected his health. One day, he accidentally dropped rubber mixed with sulfur on a hot stove, and found out that instead of getting charred and burnt, the rubber becomes hardened. Without knowing, he actually had cross-linked the rubber, but he failed to get his patent in the first place. Sadly, he died with $200,000 debt. The cure site, generally the unsaturated carbon-carbon bonds in natural rubber. The sulfur will abstract the allylic hydrogen from the carbon near the carbon-carbon double bond. It is abstracted by the sulfur and leaves a carbocation that is prone to be attacked by another sulfur radical. During vulcanization, this sulfur ring will break down into smaller parts, and it is really reactive. The sulfur radical can attach themselves at other cure sites contain carbocation, thus forming bonds between chains. The number of sulfur atom in cross-linked has a strong influence on the physical properties of the final product. A short sulfur atom in cross-link will give you a very good heat-resistance rubber, while high number of sulfur atom will give you a very good dynamic properties but with lesser heat resistant. These dynamic properties are very important for flexing movement of the sidewall of a running tire. Without this good flexing properties, this movement will lead to crack, and ultimately to the failure of the rubber product. The cold vulcanization is performed with the treatment using a bath or vapor of sulfur compound, developed by Alexander Parkes in 1846. This vulcanization can also be accomplished with peroxide, gamma radiation, and several other organic compounds. The finished product is not sticky like natural rubber, hardened in cold weather and soften upon warming except with a great heat. It is also displays elasticity, springing back into shape when deformed, instead of remaining deformed as unvulcanized rubber. We can see that the vulcanized rubber also highly resistant to abrasion and to gasoline and most chemicals. It is also possesses good insulator against electricity and heat. Both synthetic and natural rubbers undergo vulcanization. This invention has geared up the industry, especially in the automobile industry. Now we look into the differences between cross-linked rubber and thermoplastic elastomer. As for cross-link rubber, I hope you still remember that it will lead you to the thermoset elastomer product. This cross-link rubber or thermoset elastomer bond to each other through covalent bond. It is also does not melt, unprocessable and non-recyclable. In terms of the thermoplastic elastomer, the polymer chains are held together by weaker bonds such as dipole-dipole interaction. Thus, it is easy to melt it, processable and easy to recycle. One of the major differences between natural and synthetic rubber is the presence of proteins in natural rubber. Natural rubber latex (NRL) consists of a colloidal emulsion of rubber globules or particle. Latex is a term that can also be used to refer to any rubber-like polymer in emulsified form. For synthetic rubber, it is called synthetic rubber lattices. Most lattices are white but dry to a fairly clear transparent appearance like thin milk. They are not very popular, except for certain application. NRL remains of particular importance in the rubber industry, because it is still the main raw material for manufacturing operations such as dipping gloves and balloons. Nowadays the use of synthetic rubber lattices in the dipping process is increasing. Latex is referred to as any polymer in a water-based liquid or viscous state. It doesn't refer to natural rubber latex solely. Natural rubber refers to all materials containing natural rubber in their formulation. Natural rubber latex is a milky fluid that consists of extremely small particles of rubber, obtained from plants, and dispersed in aqueous medium. This natural rubber latex can be used to produce gloves, catheters using processes such as dipping, extruding or coating. Dry natural rubber is produced by DNR process, which involves the use of coagulated natural latex in the form of dried or milled sheets. Products are formed from dry natural rubber by compression molding, extrusion, or by converting the sheets into a solution for dipping. Example of products that may contain dry natural rubber are syringe plungers and vial stoppers. We have to know the percentage and the compositions of natural rubber latex. Natural rubber latex consists of 35% of rubber hydrocarbon polyisoprene. Other 2% consists of proteins. Quebracetal takes up around 1%, and another 1% consists of styrene, fats and soap. Water takes up almost the largest part of its composition, which can be found around 60%. We have 0.4% of inorganic, which is phosphate as the minor composition. Protein acts as stabilizer. It is quickly hydrolyze and putrefy, unless protected against bacterial action by the addition of proper preservative, like ammonia. Enough protein and soap remain imparts stability to the emulsion. Without the additions of preservatives, the latex will quickly darkens and coagulates spontaneously, due to the actions of acid from bacteria and enzymes. To use ammonia as the preservative, we have to look at the advantages and disadvantages. The advantages of using ammonia are inexpensive and easy to use. Ammonia is highly volatile, thus, it is easy to remove it from the product. One of the disadvantages of ammonia is that it has odor. It is also sensitive to zinc oxide. Ammonia preserved latex undergoes marked thickening when compounded with zinc oxide. Excess ammonia has to be driven off before the latex is used for compounding. So as the conclusion, synthetic rubber used as alternatives for natural rubber, and it gives comparative properties to its natural counterpart. Vulcanization also make rubber harder and rigid, as the number of sulfur employed will affect their properties depending on our requirements. Non-sulfur vulcanization produced recyclable thermoplastic elastomer by forming a temporary cross-linking. Both natural and synthetic rubbers are the important raw materials that gear up the industries. These are my references and the image credits. I think that's the end of my lecture. Thank you for now.